As most of you know, artificial neural networks are a key technology that's enabling everything from Amazon's almost magical Alexa Echo devices to Tesla's and other car companies' drive towards full autonomy. But how do artificial neural networks work? What kinds of ANNs are there? And why are they so good at what they do? Let's find out. Hey y'all, it's Dr. Know-It-All. In part 1, we are going to touch on the history of artificial neural networks, which dates way back into the 1950s and maybe even a little bit earlier if you think about it, and then explore how a simple artificial neural network, historically termed a perceptron, as it was first used for visual perception, works. So definitely make sure you subscribe to this for more, and also click the little bell icon and say all so that you get notified when more of these episodes come up. Let's start with a brief history of artificial neural networks. They started way back at the dawn of computing itself in the 1950s, early 1950s. And of course, we can rewind the clock even a little bit more and start with Alan Turing himself and the Turing test, because this is a test he came up with to formalize the status of a thinking machine. In other words, can it fool a human being into thinking there's a person on the other side of the screen? But also, Turing-complete machines are what computers still do today. They still are Turing-complete machines. A great deal of this early thinking was logic-based, and much of what we know of early computing, of course, is just that. It's very logic-based. But there were people who were more interested in modeling the human brain even back at that time. A pioneer of modeling the human brain was Gray Walter. He developed ELSI, which could move about and used a primitive vision system to actually steer and go through obstacle courses. Walter was not a computer science person, or at the time he would have been an electrical engineer because they didn't really have computer science back then. But anyway, he was instead a neurophysiologist. So in other words, he was interested in the human brain and how it worked. So he built a simple model to help him figure out how the brain works. Pretty cool. If we move a little bit forward to 1957, we get to Frank Rosenblatt and his colleagues. They developed the first perceptron, and this is the first recognizable artificial neural network. So Rosenblatt was a psychologist, so again, not a computer science kind of guy. So he was interested in the functioning of the human brain over the formal logic and math that was commonly associated with early computer science people. And as an interesting side note, early computer science artificial intelligence people, the ones that get the lion's share of attention, were the ones who are logic-based. So it was like solving puzzles or playing checkers or playing chess or something, which is all very logic-based, at least at the time. So these people were kind of a little bit on the sideline who were modeling human brains, and now that's become a big, huge focus of machine learning and artificial intelligence. The original perceptron iterations were complex blends of digital and analog circuits. Like they were actually wired together with potentiometers and stuff. Yikes, it looks really, really ugly. But somehow they managed to do it. So these early perceptrons could sort items into, say, triangles and squares. It was very rudimentary, but it established the foundational artificial neural network concepts. The concept of feed forward, which means you process something forwards, and then back propagation, where you back propagate the errors back through the network again. And also, very importantly, they established that you need to use nonlinear activation functions, which we'll talk about more later. There was a lot of promise in this early area, but the problem was the exponential growth of complexity with each new node added made this really an intractable problem with the given technology at the time. So artificial neural networks, perceptrons, etc. kind of fell out of favor. Fast forward a bunch of years to the 1980s, and we get to researchers like Geoff Hinton, who's very famous now. He works at Google. They used the massively increased power of contemporary computers to create much deeper, more complex digital neural networks. So they didn't have analog stuff anymore. So it worked a lot faster too. These researchers also developed the idea that you needed to use the sigmoid curve, which is kind of like an S-curve. Weirdly enough, I just talked about an S-curve adoption in my previous episode, and the sigmoid looks just like that. It's an S-curve. Anyway, they used the sigmoid curve because it's nonlinear as an activation function. And they came up with the partial derivative chain rule method of backpropagation, which allowed computers to learn in a much more rigorous and effective manner than before. Again, they had some amazing success with small kind of like toy problems, but they just couldn't expand this to large scale. Again, the models were too complex to fit into memory. Computers were too slow. The size of real-world problems like image recognition had far too many inputs for the processing speed and the memory of the time. And additionally, there were data problems. The data sets were simply too small to properly train these devices. You have to think back to this time. There were no digital cameras. There was no easy digitizing process. So every piece of data had to kind of laboriously and be entered by a human being, more or less. So it was very complex. The data sets were small, and it was just the computing processing power was just not quite there yet. So throughout that time, Geoff Hinton and others were shunned in the AI world. It's really true. They were shunned. And so artificial neural networks once again kind of disappeared into the background in the shadows through the 80s and the early-ish 90s. But of course, computers got faster and memory got cheaper, and digital inputs like cameras and scanners and things became commonplace. So by the late 1990s and early 2000s, we had much faster computers. We had massive storage, both RAM and hard drives. And just as importantly, we had a way of digitizing mass amounts of data. MNIST is a good early example. That stands for Mixed National Institute of Standards and Technology Data. It's a set of handwritten digits. They had 60,000 training and 10,000 testing images at a whopping 28 by 28 pixels, like that big. So, right. Anyway, this was a massive data set by those days' standards. Nowadays, we have millions and millions and millions of data points for a lot of these training things, but 60, 70,000 was a huge data set for the time. And actually, this is still used as kind of a test bed example. So if you build a new model or something, you can test it against MNIST to see how it does. And it gives you a good sort of baseline for how well your model is performing. So as we move into the late 2000s, Hinton, Jan LeCun, and others began to research using convolutional neural networks to help with model complexity. So these are really key to how modern day artificial neural networks work, but that's the topic of a future video. Artificial neural networks really came to prominence around 2012 when supervision, which was an ANN developed by Hinton and his colleagues, crushed the ImageNet competition with a much, much higher image recognition percentage on a 1.2 million image dataset than any other machine learning technique of the time had ever scored. And as they say, the rest is history. After that, artificial neural networks have been the darling of machine learning. Hinton, LeCun, and others, Hinton, by the way, is at Google, LeCun is at Facebook. They've finally gotten the recognition they very, very much deserve for all of their hard work. So that's the super brief nutshell version of artificial neural networks. In a moment, let's take a look at how a simple ANN works, but first, if you enjoy this video, please do like it so other people can find it, because that's how YouTube's AI algorithm works. And definitely, if you want to catch the rest of these episodes, make sure you subscribe. Also, a big shout out to my patrons on Patreon. It's been a good journey so far, and it's been fun talking to you on Patreon and on Discord as well. And a big thank you to Zenly Music for his introduction and concluding music with me. I know the music he did for me is silly, but he's an amazing composer, so definitely search for him in the description, or just look for Zenly Music on Instagram or YouTube and show him some love. And finally, if you're in the market for a new Tesla, you can use our referral link below. If you purchase a Tesla through that link, you get 1,000 free supercharger miles, and so do we, so that's awesome. So now that we know a little bit about how artificial neural networks came about, let's look at how a simple one is constructed and how it works. There's going to be some math in here. I promise you don't have to know it if you don't care about it. For this first example, we're going to look at about the simplest ANN we can construct. Again, this is often referred to as a perceptron because of the historical aspects of it. In this case, we have 3 layers. We have an input layer with 2 nodes. In this case, we have an output layer with 1 node, so that's the X and the Z layers, and then the Y layer is a hidden layer. This layer is not exposed to the user. In other words, it's not input nor output, which is why it's called a hidden layer. For large models, for large ANN models, there can be hundreds of thousands or millions of inputs. There can be 20 or more hidden layers between the input and the output layer, and there can be 1 to millions of output nodes as well. So again, we'll get to that stuff in future episodes. For now, let's just concentrate on a little baby artificial neural network. Of course, everything with computers is numerical. So the inputs are numbers. Even if it's like a picture of a cat or something like that, you take the numbers that represent what the pixels look like and you feed that to the ANN. Each node gathers information from all connected incoming nodes. It multiplies the values of the inputs by a weight, W sub x, and it adds this to a bias amount, something that's always on, even if there's no input. It goes through a nonlinear activation function, in this case a sigmoid, and the output is between 0 and 1. If you look at the graph, you can see that there's never any possibility of an output greater than 1 or less than 0. Generally speaking, it's good if the sum of all the inputs adds up to between -2 and +2, as that's the most linear part of the sigmoid curve. A negative below 0 value is an inhibitive value. In other words, it tends to make the next node weights get reduced. And a positive value is an inciting value. In other words, it tends to make the next node weights get increased. So if we move through the inputs to the outputs, we get all of the values, we sum them up, we move to the next node, we add everything up, we move to the next node, we add everything up, we get to the output node. At the output node, is it a negative value or 0? If that's the case, then it's a negative answer. In other words, let's say not a dog or something. Is it a positive value at the end? Then that's a positive answer. In other words, it's a dog. This process of going from inputs through the hidden nodes to the outputs is the feed forward part of the process. When the network is right, really nothing much happens, right? It answered correctly, so everything's chill. When it's wrong is when something interesting happens. So therefore, if it's trying to identify a dog and it says this is not a dog, but it is a dog, then we have an error, and that error has to be distributed to all of the nodes throughout the artificial neural network that made the mistake in some fashion. This is the back propagation part of the process, and that's like how do you do that, right? So how this is done is very cleverly using partial derivatives, the chain rule, and the fact that the derivative of the sigmoid is simply the sigmoid times 1 minus the sigmoid. I'll leave links down below. You can actually look at the derivation of all of this. That's way beyond the scope of this video. So super briefly, a partial derivative is the derivative of a given direction in a multidimensional space. So in 3D, you could have partial derivatives in x, y, and z, the 3 dimensions of space. If you don't know what derivatives are, they're the slope of a curve or the tangent. Don't really sweat it. You just kind of have to trust that I'm correct about this part if you don't know what they are. If you do, and if you know what a partial derivative is, then this stuff makes hopefully good sense to you. And in general, the chain rule for derivatives says that if you want to find dy over dx, you can do that as dy over du, which is like the hidden layer or something, times du over dx. So in the case of our input to output simple perceptron artificial neural network, we have x is the inputs, we have y as the hidden layer, and we have z as the outputs. So if we want to find dz over dx, which is the error in z, the output, over the error of the input, we can do dz dy, which is the hidden layer, and then dy dx. So we can move backwards through the chain using partial derivatives and the chain rule to figure out what errors need to be distributed throughout the network to improve its performance. And therefore, we can use this clever technique to determine what the error is for every one of the nodes. It gets complex really, really fast because you have to do this for every node and for every weight and even for the bias nodes. It's crazy. And of course, this is where very fast computers with large amounts of memory come in. And as it turns out, GPUs, or graphics processing units, are super good at this. I have an episode about that up here. So once we calculate all the errors, we then adjust all the weights of all the nodes, and we go back and try this over again. One very important note is that we need to add a learning rate factor in here to slow down the changes. By default, these partial derivative changes create really, really big steps, like they make big changes at each step. So what we need to do is multiply by a small number, like let's say 0.1 or like 10%, something like that, to make the changes 1/10 the size they would have been otherwise. This slows the training down and it makes it a more controlled process, and you don't tend to overshoot. So you get a more monotonic learning rate where it's reducing its error monotonically. Otherwise, you would get something where it went way down, way up, way down, way up, and it would oscillate. So to control it, you have a learning rate factor. Now let's talk about epochs. If we have, say, 1,000 pieces of data and we run the artificial neural network model over all 1,000, we have trained one epoch. Normally, we need to train a good-sized data set, dozens to thousands of epochs to get a well-trained model. So again, this takes a lot of computing power, even for very simple ANNs, which is a big reason why it wasn't really possible to do this on real-sized data sets until very recently. And also a note about data. we can't train on all the data. We need some for testing and also some for validation. So this is data that we need to set aside and not train on at all, because otherwise the network could just memorize the entire this data set. One really good example is serial numbers. So let's say you had like a spreadsheet with all these really interesting factors about a disease or something, but then you had a patient identification number, which was just a serial number. If you leave that in there and you train on all the data, then basically the model can learn like, oh, this serial number means that person has the disease, and this serial number means they don't have the disease. And that looks great. You've got 100%, like it works perfectly, but then you give it a new serial number and it completely falls apart. So you have to be really, really careful about saving data to the side for testing and validation. So often this is a 70-20-10 split. So you have 70% for your training, you have 20% for in-training testing, like at the end of each epoch, and then you have 10% left over for validation at the end, which is never ever used. It's just used to validate the model. So if we had our 1,000 pieces of data, we would train on about 700 selected randomly from the data set. We would then test after each epoch on 200 of these pieces of data to check it out. And then at the end of the whole thing, we would validate on the last 100 pieces of data. If your test and validation predictions are close to your training predictions, you probably have a well-trained model. So congratulations. All right. So even with a really simple ANN, it gets complex really fast, right? So stay tuned for the next episodes because it really gets nuts after this. Okay, thank you so much for watching this. Please, if you enjoy this, make sure you like and definitely subscribe so that you can catch the next episodes. Also, I promised I would give a quick shout out to the first person who identified that mask over there. That would be James O'Connor, so gold star to you, man. It is Sleep No More, which is a art, dance, theatrical production that has been running in New York City and I think also in London for quite a while. I don't know with the whole pandemic situation what's going on right now, but it's an amazing thing. It's based on the Shakespeare's play Macbeth. Highly, highly recommend it if you have not seen it yet. Also, a huge shout out to my wife. As you can see, we've got floating shelves, we've got nice decorations. She's done an amazing job, so thank you to her. I appreciate that. Looks way better than it did just a couple weeks ago. And finally, just a quick note about going on vacation. This week is Thanksgiving week, so I'm going to probably not release as many episodes as usual. I do, however, have a plumbing episode, which I think will be super useful for people, and with the holidays approaching especially. And I also have a video that I did a little while back that I'd love to show you guys, which is me climbing the Matterhorn and how to go about doing this. So hopefully you will enjoy those different kinds of videos during this coming week. If anything exciting happens in the news, I'll try to put one out, but I will be traveling this week, hopefully safely, geez. So anyway, I will definitely see you at the end of the week, about a week from now when I get back, and we will continue with our regularly scheduled programming. Until then, definitely ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.